Okay, so my talk is on the evolution of stellar spin in systems where the host star has a binary companion, and how this binary companion can perturb the orbit of the planet, cause high eccentricity migration through the Kozai mechanism, and I'll discuss the spin orbit dynamics of the planet and star during the high eccentricity phases. This work is in collaboration with Natalia Storch, another graduate student at Cornell, and Dong Lai. And it's based on these two papers here. So Storch et al., which hopefully will be on the archive in a couple of weeks, and Anderson et al. In preparation. So I'll start just by providing some background and reviewing the Kozai mechanism and how you can produce a hot Jupiter from that. Then I'll discuss the stellar spin orbit dynamics, and then end with some observational implications. So we've heard quite a bit about this already, so I won't dwell on it, but just to remind everyone, there are a lot of hot Jupiters with significant stellar spin orbit misalignment angles, which are shown here, the projected spin orbit angle versus the semi-major axis. And so you can see that there are quite a few planets with very high obliquities and some that are even retrograde. And so we want to understand the dynamics behind producing these misalignments. There are several ways of doing this. So you can have a sort of primordial disk misalignment, also planet-planet interactions and scattering. And then what I'll be focusing on is Kozai oscillations from a distant stellar companion. So just to review, imagine a hierarchical triple system consisting of a central star, a planet in orbit at about a few AU from the star, and a distant companion, so say about 200 AU away, a few hundred. If the orbit of the two stars is inclined relative to the orbit of the planet and star, the planet gets perturbed by the tidal potential. This causes long-term variations in the planet's orbital eccentricity and inclination, which looks like this. So this plot is showing 1 minus the eccentricity as a function of time. This plot here is showing inclination as a function of time. And so you can see that the eccentricity and inclination just oscillate indefinitely. And if the inclination is very high, the maximum eccentricity can be very high, greater than 0.99. These Kozai oscillations occur at this characteristic frequency, omega dot k, which is roughly given by the mass ratio of the binary in the host star, the planet's semi-major axis over the binary semi-major axis cubed, times the planet's mean motion or orbital frequency. And for the parameters that we are interested in, so a planet at a few AU and a binary star at a few hundred AU, the time scale for these Kozai oscillations is of order 1 million years. Now in reality, there's a lot more than Kozai going on. So there's additional periastron advance due to short-range forces during these high eccentricity phases. So the most important one being GR, but also static tides and stellar and planetary oblateness. And then, most important for producing a hot Jupiter is tidal dissipation within the planet. So just to summarize, to make a hot Jupiter through this high eccentricity migration, you have to pump up the planet into a high eccentricity orbit. This also changes the orbital inclination. Then tidal dissipation during the high E phases causes the orbit to shrink. And if you combine these two effects over many Kozai cycles, it can result in a planet in a few days' orbit from its host star. So this is sort of the standard picture behind this Kozai high E migration, and this has been looked at in lots of detail by other groups. And so what our group is interested in is understanding the spin in spin orbit misalignment. So we know that during this Kozai cycle, the planet orbit is changing in both eccentricity and in the inclination relative to this outer binary orbital axis. And so we want to know what is going on with the stellar spin. It definitely is not just sitting there doing nothing. It's interacting with the planet. So basically, to understand this, the star is spinning. This causes it to be oblate. This causes there to be a mutual torque between the planet and the star. And as a result, the stellar spin vector, which is drawn here as this red arrow, this stellar spin vector S will precess around the binary orbital, or the planet orbital angular momentum, which is L. And it precesses at this frequency that we're calling omega ps. And this just depends on the stellar spin rate, the planet mass, the semi-major axis, and you can see that it is a very strong function of eccentricity. So that's what's going on with the star and its interaction with the planet through the spin-orbit coupling. In the meanwhile, as I said, the planet is doing its Kozai oscillations. So the orbital angular momentum axis L is precessing and also nutating around the binary axis LB, shown here in black, which we are taking to be fixed. This vector L precesses at this frequency that we call omega PL, which is approximately 1 over this characteristic Kozai time scale that I introduced earlier with this extra eccentricity dependence. So put these two together, so we have, just to remind you, we have this blue vector L precessing around LB at this frequency omega PL, while S, the stellar spin axis, is simultaneously precessing around L at this frequency omega ps. And in particular, we are interested in the spin orbit angle theta SL, and then there's also the angle between the stellar spin and binary axis theta SB. So we want to know what happens when you put these two things together. So we expect these three qualitatively different regimes of dynamical evolution. The regime depends on the relative values of these precession rates, omega PL and omega PS. And remember that these are both very strong functions of eccentricity. And the eccentricity during a Kozai cycle is changing from being nearly 0 to nearly 1. So both of these frequencies are changing a lot. Okay, so the first regime is where omega PS over omega PL is less than 1 throughout the Kozai cycle. And so in this scenario, the planet angular momentum L is precessing around LB extremely quickly. And so S, the spin vector, basically cannot keep up with L and essentially sees a time averaged version of L. And so effectively what happens is S precesses around LB, and so the spin binary angle theta SB is approximately constant. You can also imagine the opposite regime where omega PS over omega PL is larger than 1 throughout the entire Kozai cycle. In this case, the spin orbit coupling is extremely strong, and so as L is precessing around LB, S essentially will follow L. So no matter what L is doing, S follows it. And in this regime, the spin orbit angle we expect to be constant, theta SL. And then finally, you can consider something in between these two extremes where omega PS over omega PL is equal to 1 at some point during the Kozai cycle. And in this case, we have a secular resonance, and so the behavior can be extremely complex with the possibility of chaos. And so we don't have a priori a good intuition of what the dynamics will look like in this case. But here's an example. So this is this regime 2 that I was just talking about. So in this top panel here, I'm showing 1 minus the eccentricity as a function of time. So this is just the regular Kozai cycles, and you can see that they're nice and periodic looking. In the bottom panel, I'm showing the stellar spin-orbit misalignment angle, theta SL, and you can see that it's doing completely unpredictable things, very irregular. This plot is actually showing two different systems with nearly identical initial conditions. So one is in blue and one is this dotted green line. And so these two trajectories differed by about 1 part in a million at t equals 0, but then you can see after about 100 million years, they are diverging significantly, which shows that you can have chaos in this regime. Okay, so for a given system, we want to know what regime that we expect to be in. So this ratio, which determines that, omega ps over omega pl, it scales as the planet mass times the stellar spin rate over the semi-major axis to the 9/2. And so from the scaling argument, we can expect that massive planets and or rapidly rotating stars to be in the adiabatic regime, where S is following L with theta SL equal to constant. So this is just showing what happens when you include tidal dissipation in the planet and also stellar spin down due to magnetic braking. And the thing to notice here that is even if a system starts out in the non-adiabatic or trans-adiabatic regime, they will all end up in the adiabatic regime once the semi-major axis decays due to tides, which you can see here. And so the spin-orbit angle settles to a final value. Now actually predicting that value, though, for a given system is not always possible because of this chaos. And in this plot, I'm just showing the final spin-orbit angle as a function of the planet mass for a bunch of systems with nearly identical initial conditions. And so you can see that, again, there's a large spread in this final misalignment angle, which is a signature of chaos in this regime. Okay, so what are the observational consequences of all this? So we looked at the distributions of this final spin-orbit angle for a bunch of different parameters. So we started by looking at the dependence on the planet mass, since this determines which regime of evolution we're in. So in this top panel, so I'm showing histograms of the final angle. And in the top panel, this is showing a 1 Jupiter mass planet. I'm holding all of the other parameters fixed just to get an idea of how important the planet mass is in the final distribution. So I'm setting the binary separation to be a constant 200 AU, solar type stars, and stellar spin down using the Skumnich law calibrated to be similar to the sun, and a semi-major axis of 1.5 AU. So you can see this interesting bimodality for lower mass planets, which gradually starts to go away when you increase the planet mass. And then finally, for a planet mass of 5 Jupiters, nearly all of the systems are aligned with just a few others that are significantly misaligned. And so, does this make sense in terms of our theory of these different regimes of evolution? Yes, it does, because remember that this ratio, which to be adiabatic so that theta SL is constant, we want this, so this scales linearly as the planet mass. And so that makes sense that you would have all these aligned systems. Okay, so that was just for one semi-major axis, but in reality, we don't actually know where planets typically start out in the disk. And so we looked at a wide range of, a distribution of semi-major axis in this range here. And you can see that the overall results don't really change too much. So you still get this bimodality for lower planet masses and a preference for alignment for higher planet masses. We also changed the stellar properties. So this is the plot that I showed you before for a solar type star. We also looked at a more massive star, basically an F star, and adjusted the spin down rate so that it is spinning more quickly, as we would expect and as we heard about in one of the other talks. So you can see that for lower planet masses, the qualitative distributions look pretty similar, but once you start to increase the planet mass, they start to look very different. And so this tells us that in addition to planet mass, the stellar spin properties and history can be extremely important in the observed distribution of misalignment angles. Okay, so our main conclusions are that the stellar spin evolution, which was sometimes not really focused on in previous work, actually plays a really important role in this spin orbit evolution and needs to be included. The variation of the stellar spin is actually much larger than the variation in the planet's orbit angle, and so that needs to be considered. There are these three qualitatively distinct regimes of evolution with the possibility of chaos in the stellar spin vector. And finally, that the overall distribution of final spin orbit misalignment angles depends pretty strongly on the planet mass and the stellar spin properties and the spin history. And so this should be focused on in future work. So I'll stop here and thank you and take any questions.
Thank you, Kassandra, for a very interesting paper. Tim Bedding first.
Thank you, it's fascinating. A star is not a solid body and doesn't spin as such. Do you have anything to say, or can you say something about internal rotation? In particular, can the spin axis of the star change as you go from the center in towards the middle?
Well, we were treating it as just a rigid body, and I think there's some disagreement over whether that, how much variation that you would expect in terms of that. So, I mean, it's definitely something we could look at in the future, but at present, we're just treating it as a rigid body. Right.
Yeah. I had a question concerning the spin down law that you use for your star. You mentioned the Skumanish law.
Yes.
How are your results depending on this law? Have you used another one, just like the Cavalier law, or which is a bit different, or maybe the Mattertal law, which are more precise or more specific spin down laws? Do you know what would be the dependency on your results?
So we haven't looked at that yet. It's definitely something that we plan to address in the future. I would expect that the results could definitely change, because even changing the parameters in the Skumanish law, so basically the initial spin period and the other free parameter, that can significantly change these final spin orbit distributions. And so, yes, I would imagine that the stellar spin down law could affect these things.
Yes, I was wondering about the range of orbital distances over which this mechanism will be important, operative. And when we're observing planets in circular orbits that are misaligned, up to which orbital distance can you invoke this mechanism versus others?
For the planet or star?
Planet or star.
Like binary separations from the companion? I'm not sure I understand the question.
Planet-star separation. I mean, you need the planet to be close in so that it's affected by the oblateness of the star, and then it interacts. So presumably you can't do that at 0.2 AU or 0.1 AU.
Right, because
Right?
so you need to have the planet be far enough away so that the Kozai cycles can pump up the eccentricity pretty high. So basically anywhere in the range of about 1 to 5 AU can work depending on the separation of the two binary stars.
No, but you need the apsis to be, the periapsis to be very close to the star. You need a high eccentricity, and you need,
Right.
and then the thing will be circularized.
Right.
So if we observe a circular planet at 0.1 AU or 0.2 AU that is misaligned, probably your mechanism cannot be invoked as an explanation. Is that right, or maybe I'm missing something?
Well, that could be the final end state of one of these high E migration cycles. So, I mean, not all planets will end up as hot Jupiters, but they can end up as warm Jupiters with a non-zero misalignment angle. So I think it still could work.
We've got one last question.
Sure.
Sri, are you addressing this? Yeah. Okay, I want to take a question from Stefan, so please, a quick answer. I know this comes right out of your youth. You've used this your whole life.
Yeah, I just want to emphasize the previous question that this is can apply only for certain distances of the binary and certain distances of the planet from the
Correct.
star. So are you claiming that all the systems that we see with misalignment are a result of that? You have to put a binary at a certain distance in order for that to work for all the planets.
No, we're definitely not claiming that it explains every misaligned hot Jupiter that's been observed because, well, first of all, you need to have a binary companion. Then the inclination of that binary companion has to be high enough, and then, as you point out, the orbital separations have to be just right. So I can't really give a quantitative answer as to like a percentage that we would expect to see, but it's definitely not all of them that can be explained.
We have a last comment.
But definitely, it's a wonderful idea. Thank you for that.
Last comment from Stefan, and probably don't answer it, Kassandra, because we've run out of time. Just let him say.
Yes, it's just a quick comment on the question you get by Tim on the action of tides on the internal rotation of stars. In fact, both tidal inertial wave in the convective envelope and tidal internal waves in the radiative core are able to transport angular momentum and to modify the rotation profile. So it can be probed by asteroseismology. What we have to answer is how is the competition between tidal action and convective transport of angular momentum and tidal excitation of internal waves on the one by stochastic excitation.